Hello, good evening. Again, I am going to send you, my dear students, in DE class, differential equation classes. Um, the other topic that we're going to discuss today would be mixture problem. It's one of the applications of differential equations as well. There are two other topics that I will be sending you. This is about circuit problems and mechanical spring for mechanical engineering. Okay, so mixture problem. Now, when you say mixture, more often these are, say, a container. If you can see my illustration, sorry for putting it here on the problem statement. So if you have a container, for example, and then you put in something in it, okay, you put something like a solution. What could be the solutions? It could be sugar solution, water, and sugar mixed together. As you put in, of course, there is a rate by which you put in, that is the charge. And you will also have a discharge here out. So you have an inflow, Q in, and Q out, outflow, right? So it's always like that. It can also be brine solution, salt and water, sugar and water, and other solid that will be dissolved in liquid. And when they mix together, they will become um, fluid. And of course, like densities will be there and so on. But we are on the mixture, how many um, kilograms of salt, how many kilograms of sugar will be in the water that will discharge, something like that. So, without much ado, then let's take an example. Let me just get my charger. Sorry, because you know how old my laptop is, so it keeps on discharging. Okay, so you can skip this part, okay? All right, so here is a problem that we're going to do. A 100 liter, oh dear, a 100, what's happening? Okay, here we go. A 100 liter, hey, it skipped like that. My laptop is tired. A 100-liter tank, 100-liter tank. So what is that? That could be the volume, okay? The volume of a tank. A 100-liter tank initially contains 20 kilograms of salt dissolved in water. Okay, so here are my initial. I have already solved it, so I just have to disseminate it. The initial amount of salt here is 20 kilograms, and the initial volume of water is 100 liters. You can put an S there if you want. Brine is the name of the solution that has salt and water. Okay, salt plus water is called a brine. So the brine containing 0.5 kilogram of salt per liter flows into the tank at a rate of 3 liters per minute. Let me just shade all these ones here. So the the consistency or the combination of the water and the salt is zero point 0.5 kilogram of salt per liter flows into the tank. Okay, so we have a brine, zero point 0.5 kilogram per liter, and that goes into our tank. And we have 3 liters per minute as the rate for it to go inside the tank. I am just going through the problem statement. Okay. It says further that the well mixed solution flows out at a rate of 2 liters per minute. So that is the outflow. The inflow is a 3 liters per minute. The maximum capacity of the tank is 160 liters. Okay, write the differential equation governing the amount of salt, A of t in the tank. Solve for A of t, the amount of salt in the tank at any time t, and use this setup to answer the following 10 multiple choice questions. So I have multiple choice questions underneath. So the scenario here is you have a tank, I repeat, and there is a brine solution that goes inside the tank. There is a brine solution that goes in at a rate of 3 liters per minute. If you say brine, this is salt and water combined. Okay? The amount of salt inside the tank has originally 20 kilograms, and the amount of water inside initially was 100 liters. And as the brine is filled into the tank, there is a rate of 2 liters per minute solution that goes out from the tank. Okay, this is the one that I was saying last time, that when you say solution, then this is a combination of one material with the other that are liquid. That's why when you say, Mom, can I show my solution? Where will I show my solution? Solution is actually a combination of two fluids, right? But we always say the word solution when we say the workings. So I'm going to correct you with that terminology, my dear students. Solution, this is a combination of two fluids, okay? Right. The solution would be, now I'm using the word solution. Okay. So let's change that to workings because that's is always what I hear, solution. So I use that. Okay. So now we have the workings here. The general formula to solve for a mixture problem in differential equation is the difference in amount. The difference in amount over t dt with respect to t is equal to the rate inflow minus the rate outflow. Okay, but rate inflow is defined as the concentration that goes in this particular question it is the brine solution. Okay, so the concentration that goes in times the rate in going in minus the concentration out. The concentration out times the rate out. Okay. Now, what is the concentration in? It is 0.5 kilogram per liter. This was in the question, 0.5 kilogram. So 0.5 kilogram is the concentration that goes in. The rate by which it goes in is 3 liters per minute. That should be multiplied together. Why? Because what we want is the difference in amount. So the L and the L cancels out here, giving you only kilogram per minute unit. And and 0.5 times 3 is 1.5. Now let's go into the concentration out times rate out. The concentration out that we do not know at this point in time times rate out, that is 2 liters per minute. How did I know that? 2 liters per minute, it says here, flows out at a rate of 2 liters per minute. So the general solution, the general equation will be dA over dt is equal to 1.5, 0.5 times 3 is 1.5 kilogram per minute minus A of t over V of t times 2. What is this A of t over V of t? This is your concentration in. Concentration out, sorry. Let me just write it down. Okay. So this is concentration out. Okay. A of t over V of t. We will be using this formula later. Okay, so let's concentrate first with the 1.5 minus A of t over V of t times 2. Right. So what is V of t? V of t is VO. So there's no, okay, I'm going to write the formula here. V of t is equal to VO plus Q in minus Q out times T. Now, why am I using Q, or why are authors using Q? Because Q in fluid mechanics is about discharge. All right, it's a discharge. So you can say inflow is Q minus outflow, Q out. Okay, that is how it's being presented. So the volume at any time will be equal to the initial volume plus discharge in minus discharge out times T. So if we're going to substitute the values, our VO is 100 liters, that is in the problem, initial value, plus Q in, that is how fast the brine is getting into the container, that is 3 liters over minute or per minute, minus the discharge outflow, 2 liters per minute, times the variable T. What could be the units here? Let's investigate the units. VO VO is in liters. And you're going to add this one to liter per minute. And this is liter per minute. And you're going to multiply it with time, which is also in minutes. So the minutes and minutes cancels out. So therefore, this unit will be liters and it's added to liters. So the volume will be in a liter unit. That is if you are using liters as your volume unit. So 3 liters minus 2 liters per minute, that will be 1 liter, 1 liter per minute times T, or simply T. Okay, that's why we have V of T is equal to 100 plus T formula. Let's then substitute that to our differential equation that we have here earlier on. So we have dA over dt is equal to 1.5 minus A of t over V of t times 2. Okay, let's have a look again. So 1.5 minus A of t, a while ago it was A of t times 2. So because A is a function of t, you can just say A and then times 2 and then the V. This is now our V. V of t is a function of t. Okay. Right. So this is now our differential equations. Everything will evolve from here. Now, if you're going to rearrange that, it becomes, you have to transpose your, what happened to my laptop? It's sticking. It's not going up. Okay, there you go. So you have 1.5 minus 2a over 100 plus t here. Okay. If you're going to transpose this to the other side, then you will have transpose the negative 2a over 100 plus t. Then you will have dA over dt plus 2a of t, or simply 2a, over 100 plus t, that's the denominator, that is the v of t that we have solved a while ago, is equal to 1.5. There's no dot there, that's a period, okay? There. So this is now the general form of our differential equations with respect to t. If you're going to look at it, it follows a linear differential equations, which states that dy over dx is equal dy over dx plus p of xy is equal to qx, or q of x. So I made a comparison in this, that if our y is our a and t is equal to x, then dy over dx plus 2y over 100 plus x is equal to 1.5, thereby saying that the 2 over 100 plus x is your px and that 1.5 is your qx, as you can see from here. Moving forward, now we're going to integrate our differential equations. So as I've taught you before, we need an integrating factor. Okay, so maybe I can put a rectangle here meantime. So right, just to blind it while I am explaining, okay? Right. So the first thing we're going to do is to determine the integrating factor. I think it's not even, I don't know what's happening now. Oh, because I did not put it into arrow. Okay. So the integrating factor, as we always do, is equal to e raised to the integral of p of x. Okay. Is the integral of p of x dx. Our p of x there is 2 over 100 plus x dx. Or that is, by the rules of logarithm, you have the integral of du over u is equal to ln u. We know this very well. Okay. Now, if our u is 100 plus x, our derivative is dx. So everything is in place, thereby having an integral of 2 over 100 plus x dx is equal to ln 100 plus x. Now, the 2 can be separated, so you can do like 2, the integral of dx over 100 plus x. Because this is already a du over u, so you will have 2 ln u, wherein u is 100 plus x. All right? Okay. So 100 plus x, 2 ln 100 plus x can be simplified as your 2 here. Your 2 here can be an exponent of your u. Okay? So that would be ln 100 plus x. In this case, we are using t. X is our t. We are differentiating in terms of time, but I just have to compare it with x, which we are always dealing with. So you will have an e ln 100 plus t raised to the second power. But we know that ln e, or e to the ln, is equal to 1. So I just canceled it. And whatever is your u, that will be the equivalent of e to the ln u. That's why I just have copied 100 plus t square underneath. Let's continue. Now we're going to do the integration. So the integral of dA over dt is equal to I over 1 over ix. 1 over the integrating factor, which is 100 plus t square. And then the integral of qx ix dx plus c. There you go. So the integral of dA over dt is a. equal to the integrating factor. The integral of qx is 1.5. Integrating factor is 100 plus t everything square. And all of this, as you can see, when you're going to integrate 100 plus t square, you will do plus 1 for the power. So it becomes 3. And the denominator will also be 3. So just to help you recall, if I have an integral of, have the space, the integral of x, so this will be x to the power 2 over 2. The integral of x cubed is equal to x to the power 4 over 4. But of course, the integral of x dx will be equal to x to the power 2 over 2. So same with this. It's to the power 3 because you have a dt here. You have your dt here. And your dt is simply dt. There is nothing that you're going to multiply with because the variable t is the sole variable inside the bracket without coefficients. Okay. Right. So that will be for the qx or q of x, I of x, dx, plus your constant. So your constant will just be multiplied to the integrating factor. That's why you have c over 100 plus t square. Right. So if you're going to simplify this, you can multiply everything by 100 plus t, everything raised to the second power, because this is common to both. There are only two quantities here. What are they? This. And the other one, this one. So both has got 100 plus t raised to the second power. Okay? So you have 100 plus t raised to the second power. A is equal to 1.5 over 3, 1,000. There's a missing 0. Plus t cubed plus c. Oh no. It's not. I copied a different one. Okay, so it's 100 plus t there. So here will be 1 0 only. 2 zeros only. There. Okay. It's 100 plus t. There. It's not 1,000. Sorry for the a lot of zeros. For the so many zeros. Okay. So let's continue. 1.5 over 3, 100 plus t cubed plus c. And you multiplied everything by 100 plus t, everything raised to the second power a. And this is what we got. Okay. So a now is equal to 1.5 over 3 plus this one. Okay, the numerator over the denominator, because you are going to kick this out from the left side of the equation, thereby having this huge equation here. Okay, that will be for A. Now, what you're going to do next is to find for C. This is the general solution. Okay, now you have to find for the value of A, the value of C, when T is 0. So when there's no pouring in yet and there's no discharge, outflow discharge, then that is when T is equal to 0, initial condition. A is equal to 20 kilograms. It says in the question that the container has got 20 kilograms of salt and 100 liters of water. Then after which there was a brine of 0.5 kilogram per minute that is being added, while the discharge or the outflow is 2 liters per minute, as the brine is added to the container at a rate of 3 liters per minute. So we need to get the value of C here so we can have a general solution, um, a particular solution, I should say, a particular solution where C is already substituted with a definite number. So the initial conditions would be T is equal to 0 and A is equal to 20 kilograms. We substitute. We substitute it here in our general equation, and we will get a C equal to negative 3, sorry, 3 with 5 zeros. So that would be 300,000 value of our C. Having minus 300,000 of our C, let's substitute it. 345. Yes, 300,000. Let's substitute our general equation. Then we have a particular solution of the one in orange. Yeah. So this becomes our general particular solution. Olena, I'm already sleepy. I still have 7 o'clock tomorrow. Sorry. Okay. So here you go. Right, so this is now our particular solution, okay? If you're going to simplify, then you get a simplified form, which is 0.5, 100 plus t minus 300,000 over 100 plus t, everything square. How do you do that? So the 100 here, this one, this 100 plus t raised to t, and the 100, what is the 1000 doing there? Okay, and this 100 plus t, everything raised to the third power, there will only be one 100 plus t left later. I also made a mistake here in writing two, so too many zeros for that matter. Okay, and 1.5 over 3 is 0.5. 100 plus t raised to the first power, and then minus 300,000 over 100 plus t. So this will be our working particular solution. So if you're going to solve how much salt is in the tank after 0 minute, After 0 minute, you must go back to 20. Correct? Okay, let me just do that for you. Let's pull out our calculator. So let's use this formula, okay. When t is 0, then you'll have 0.5 times 100. 0.5 times 100 only. Minus, here, it will be 300,000 over 100 square. It will be 100 square. Why 100 square? Because t is 0. At t is equal to 0, or when t is equal to 0, the amount of salt, sorry for that, it's always associated with the amount of salt, A, is equal to 0.5 times 100, because t will be 0, minus 300,000 over 100 square. Let's calculate this one. And also, my pen is not, look at that. Okay, so that will be 0.5 times 100 equals, take away, let's put that in bracket, and that is 300,000 divided by 100, another 2, close bracket, equals. There you go. It went back to 20, which is supposed to be the answer. That is the correct one. Okay? That when t is equal to 0, then you go back to the initial condition on the amount of salt in the tank. That is also one way of checking whether your differential equation is correct or not. So if you have checked it that way, then you will be able to solve correctly the values of the amount of salt in the tank after 5 minutes, after 10 minutes, and after 15 minutes. Okay? And I'm going to leave that for you to do. Right. So let me just put this one as your homework, or assignment maybe, or homework. Let's put it as homework. Okay, now we go to the 10 multiple choice questions, which will be appearing the same, or it appears the same in your final exam. So there will be a mixture problem there, and then there will be 10 related questions about the problem statement and the solutions of it. Number 1, what is the initial amount of the amount of salt in the tank? That is when A is 0. It is 20 kilograms. And that is given in the problem. That is easy peasy. By the way, when you be answering such where it's already given, then you just say in the space provided, like this one here, 20 kg is given in the problem. You must have a backup of why is it so. Let's go to number 2. What is the initial volume of the tank? That is V of 0. Again, it was given in the problem, or it is included in the problem statement. Maybe we can put that in, because given in the problem was already used in the first question. So you say it is included in the problem statement. Okay, Number three, what is the inflow rate of salt into the tank in kilogram per minute? So I have defined the rate inflow a while ago. Rate inflow minus rate outflow, and the rate inflow is the concentration in times the rate in. So in the concentration in is the zero point 0.5. This is from the brine solution. Zero point 0.5 kilogram per liter. That's the concentration. That's the solution. Rate in inside the tank is 3. So 3 times zero point 0.5 is 1.5. And that's the answer. Number 4. What is the outflow rate of salt from the tank? So this time the outflow is AT over VT times 2. When T is equal to 0, your A of 0 is 20. That's the initial. And when V of T is used and T is 0, then V of 0 is 100 liters. So using the ratio of A of T over V of T, if A of T is 20 and V of T is 100, so that will be zero point 0.2 and then double it. Where did I get the 2? The 2 is the outflow rate, the discharge. Yeah. Um, that is the rate of outflow from the outlet. Yeah. It's 2 liters per minute. So that will be multiplied to A of T over V of T, thereby having an answer of zero point 0.4 kilogram per, oh, zero point 0.4 kilogram cannot, oh shush, it's not working. I think it's already tired. Never mind, it's okay. Yeah, it's so difficult to remove it. Look at that. If it can't, then I will just do like this instead. Yeah. Kilogram per minute. Okay. Let's investigate our unit here, if that is correct. The A, or the amount, is kilogram. The volume is, that would be in liters. And the one we're multiplying is 2, which is liters per minute. So liters and liters cancels out. You only have kilogram per unit as a unit 4.4. And that's what we got for number 4. Okay. Now we move to number 5. Number 5, what is the rate of change of the tank volume? Rate of change of the tank's volume, dV over dt, the change of V. The formula we're going to use is, in any mixture problem, V of T is equal to the initial plus the discharge in and discharge out times T. I know that discharge means going out already. You're discharging, or shall we say charge in plus discharge out. Okay. Or inflow, you can say inflow as well. So this will be your inflow and this will be your outflow. So V of t is equal to the initial volume plus inflow minus outflow times time. Now, inflow is 3 liters per minute, the inflow of the brine inside the container. And outflow is 2 liters per minute. That is the rate by which the well mixed solution goes out per minute. So 3 minus 2 will be 1 liter per minute. Q in minus Q out. Okay, that is the rate of change of the tank volume, right? So that's the only thing you're going to consider um, for that particular solution. It's just the Q in minus Q out, okay? Number 6, what is the expression for the volume of the tank? V of t after t minutes. There you go. So you can use all of it now. You have V of t is equal to VO plus Q in minus Q out times t. We know that the inflow is 3, the outflow is 2, thereby having 100 plus 3 minus 1, 3 minus 2 is 1. So 1t or simply t. So therefore the expression is V of t is equal to 100 plus t. That's the answer. Number 7. What is the differential equation for the amount of salt A of t? We already have um, done this one. It says C above. Can you remember the first part that we did? The first part that we did. I'm scrolling it. Here. So A is equal to 0.5, 100 plus C. This is the particular solution. If you like the general, then you can have this one here. This. Okay. Or you can simplify further if you want to. So it jives with the answers. All right. So it's 1.5 minus A of t over 100 plus t times 2. Let me find that out again. Where's that 1.5? I have already done that a while ago, but I'm not so sure where is that particular point is. Oh, here. Yeah, it's the same because 1.5 over 3. But there's another one that has 1.5 that I'd seen in here. There you go. Okay. This is the one. Right? dA is equal to 1.5 minus 2a over 100 plus t. That is the very first part where we have to do rate inflow minus rate outflow. Where the outflow is A of t over V of t times 2. And we got that. Okay. Let's go back where we have left off. We are now in which question? Question 7 is done. See above, yeah. Number 8. At what time would the tank overflow? Okay. So we have the capacity of the tank as it's stated there. The maximum capacity, volume max of the tank is 160 liters. Okay, so V of t is equal to VO plus Q in minus Q out t. We know this very well. We have used it many times. So 3 minus 1 times t. The initial volume is 100 liters. And V of t, we can use this one as 160 here. So 160 transpose the 100 to the other side. So 160 minus 100 is equal to t. And it gives us 60 minutes. So 60 minutes is the time for the tank to overflow, or 1 hour. Now, assuming that the tank doesn't overflow, what is the equilibrium amount of salt in the tank as t approaches infinity? Equilibrium amount of salt. So you have to get the DE, the differential equation that we have formulated a while ago, and then you have to equate that to zero because you are in equilibrium amount. Okay, equate it to zero, and t approaches infinity, which will give you negligible value. So t here therefore is negligible because that approaches infinity, and you will only have 1.5 times, that would be 1.5 times a of t, that will be a variable, over 100 only. Okay, let me just put it here. So that would be dA over dt is equal to 1.5. And then a of t is still unknown, a of t, because that's the amount, equilibrium amount. That's the one that we are looking for. Over 100 times 2, so you just have to put the 2 here, is equal to 0. You have to equate it to 0. Equating that to 0, that will give you 1.5 minus 2 a's of t over 100 is equal to 0. Multiply everything by 100. So 1.5 times 100 will be 150. You have to move the decimal place twice to the right. And then minus 2 a's of t is equal to 0. Moving this 2 a's of t to the other side, you will have 150 is equal to 2 a's of t. Dividing both by 2, then you get 75. Okay? You can replay this part if you want to get the workings and how the 75 was taken. It's up to you. Okay, let's move to number 10. Number 10, if the inflow rate is doubled, how would the equilibrium amount of salt change? Okay, so what I did was you just have to double 1.5. 1.5 times 2, that will be 3. Multiply the same by 100, like so, and then divide it by 2, like so. And you get 150 kilograms, which means that it would increase by 50%. Was it 50% or 100%? Or it should be, that's not the right answer. It should be doubled. That's the correct one. It would double. Okay. All right, then. So this is all what I can share with you on mixture. And yeah, please, when we'll see each other, then you will have your sit work. Okay. I will remove this one now. Hi, and you will have your sit work on mixture. So there are two more topics that I'm going to do a video for you: the circuit and the mechanical spring. All right, then, bye for now.